Hi everyone, it's so good to see such a big turnout today. Today I'm going to be talking about the future of software. So I'm just taking you back to the past where in the old days we used to program in binary and eventually assembler came along. But there was huge resistance for some people moving from programming something like binary to something like assembler because it was like not the way you should do programming, you should do it in binary. But consistently in the history of programming, we always think that there's one way to build software, there's one computer science. But you know, in the old days, in the 70s, people were very open-minded because they had no rules and they had to invent new ways of building software. So back in 73, the good old days, C started to become a real language and started to emerge, and it captured the popular imagination. But there was this guy, Carl Hewitt, who was kind of a naysayer at the time, and he felt the problem with C was that you would allocate a chunk of memory, put stuff in the memory, read from it, write to it, and that was going to cause all kinds of problems in the future. He felt hardware wasn't strong enough to actually manage that kind of process if you built any kind of complex software. Where he was wrong was Moore's law, where hardware kept on improving, all the time, and so his worry about the hardware not coping didn't really materialize back in those days. But what he wanted to do, he actually created a concept called the actor model. And with the actor model, the actors are very lightweight objects where they could do processing. They were actually processors, really. But they could do their own processing. And all there was in the environment of actors is actors. There's no other types of software other than actors. And actors can only do their own internal process, they can manage their own state. But no actor can share state with any other actor. So memory was never ever shared on a hardware level. And so the way this works is that actors have an address, and it works with message passing. And the address is their identity, and so it's really passing messages between identities. And those messages then land in what was called a mailbox. So each actor had its own little mailbox, which was like its little mini queue of incoming messages, and then it would process each message one by one. And when it processed the message, all it could do was change state and send messages to other actors. It could also create new actors, and it could kill itself. So those are pretty much all you can really do with an actor. It doesn't really, within itself, interact with the outside world. It's just a system of actors speaking to actors, and so there are no side effects in the way that you would work with external systems. But in a way, if we look at smart contracts today, there are certain similarities in how blockchain transactions work as the actor model works. It's also about message passing. It's also quite hard to work with the external world. So Carl Hewitt really promoted this idea, but he wasn't successful in making it a thing back in the 70s. But then, in 1986, Erlang was born. And this was a language that actually adopted the actor model for the first time. And they had a reason why they did that. It started with the Ericsson company. So some people think Erlang is the first two letters of Ericsson, ER, language, Erlang. Which it may be, but there was also somebody called Erlang, I think in the 40s, who invented telephony, like rules and tactics of how telephony should work and basic protocols. So if you look at telephone companies, you have to have a switch which connects people, and people need to connect to each other, and that's on the very simple level. But you also need to have a lot of concurrency because you can have many different people going through a switch speaking to many other different people. And the systems need to stay up and be resilient. So concurrency and resilience are a key element of building telephony systems. What makes things harder is when you have multi-switch concurrency. So not only do you have people speaking to each other through one switch, you could have people routing through other switches to speak to each other. So you need quite a complex system of a complex concurrent distributed system, which has to be highly resilient. So like those are the common elements that actually drove the building of Erlang and to use the actor model. One of the other problems that the telephone company needed to think about was version control. What happens if there's an improvement in their software? Could they bring down the whole, they obviously couldn't bring down the whole network to make those updates. So they needed a way to keep the system alive while they updated it. And I think they call it hot swapping of code. In today's terms, I think we think of it as blue-green deployments. And so that also became a key part of the Erlang language. So some of the ways that Erlang manages its massive scalability is you can simply add more machines to Erlang and it'll just absorb the parallel processing. But if you have multiple cores in any machine, it'll use those too, and you don't have to write code to do that. It'll just find them through the way the language works, speaking to hardware, and just start using everything. And so it really is massively scalable. So Erlang has a VM called Beam, and every single machine in every single system runs Beam as the VM, and basically, it's exceptionally reliable. You can build fault-tolerant code and apps. You can swap out the code while it's running, but a lot of attention was paid to connecting to machines and hardware. And even to this day, a lot of IoT devices actually use Erlang and the OTP, which is the Open Telephony Protocol, as its way of actually talking. So even to this day, people build stuff in Erlang. So if you look at WhatsApp had a very small team, but they built a system that is really probably the largest telephony system now in the world, or certainly in certain aspects of it. And they actually did this with a team of about 20 people. And the way they were able to do that was to build an Erlang. They actually built the entire telephony network using Erlang. So on a single machine, you can get 2 million connections. Because it's so lightweight, all these little actors are very, very tiny, lightweight things. They have billions of connections a day, and today they send more text than every other telephone network put together. But there is a problem with Erlang. It's very obscure, and it's not a fun language to work with, and most developers don't love it. It's like weirdly functional and mathematical, and so it never got adopted in the mainstream. So along came Elixir. Elixir is a meta language, so it's a language that allows you to build other languages out of itself, including itself. If that sounds slightly recursive. So what they did, they modeled the language a little bit like Ruby to make it more accessible and easier for people to think about. And so Elixir is getting far more adoption than Erlang ever could. Elixir is still not the most popular language in the world yet, but it's a lot easier to work with than Erlang. And so there is a rise in adoption. And basically how it works is Elixir compiles down to Erlang. And so whatever you build in Elixir actually becomes Erlang. And that actually allows you to build these kind of incredibly scalable apps and systems that are highly resilient, where you could hot swap code in real time without downing your system. And now Elixir is killing it too. So Discord is written in Elixir, which effectively means it's written in Erlang. Discord is just growing massively at the moment, and the way that they can actually cope with this massive growth is because they built this using Elixir and Erlang. Bleacher Report, do you know the Bleacher Report? Okay, well, Bleacher Report it's a sports information network where they actually distribute real-time information and news around sport. Bleacher Report is actually a sister company to Trixta. We actually share a common investor, interestingly enough. And Bleacher Report were one of the main contributors to Elixir. So what they found at a certain point was they had 50 AWS EC2 instances running to kind of manage all of their information and their push notifications. But their push notifications at that point, as they were doing their processing, would take about 3 minutes to reach people's phones. And when they switched to Elixir, everything changed for them. The number of EC2 instances dropped to 5. So it was like a 10 times drop. And their push notifications went to 60 milliseconds. So it was a massive change for them. And that just kind of shows the power of using Erlang, and in their case, using Elixir as the way into Erlang. So I'm just going to give you a brief introduction into the Trixta protocol. And feel free to chime in, Roger, feel free to add anything if you like. So at Trixta, we use Elixir as the way to build out our systems, and we're looking at how can we improve and actually totally radically change the way we even think about building software. And we basically using all the models of Elixir, the actor model, and ultimately Erlang, and the open telephony protocol. And our goal is, if we can abstract the building of software into a very simple paradigm, including visual tools, we can then eventually compiles down to Elixir and to Erlang. So we can create the world's most powerful, scalable, resilient applications with hot swapping of code. And yet, in our view, we think that we can make this the easiest way to build software. And it all comes down to the concept of spaces. And so visually, we want to model systems as different contexts. And the way we see them is context within context. So in this particular case, just very briefly, this is actually a chess playing space. So the outer space, the outermost space, is the lobby of the chess site. And then inside of the lobby, we have a matchmaking space. So people may come into the lobby, want to play a game of chess, and then they'll actually find their match within the matchmaking space. And then the matchmaking space will tell the lobby that it's found a match, and then the lobby will push those people into the game playing space. So we actually have 3 separate spaces here, and there are 2 within the lobby space. But in reality, the way we model this under the hood, this is actually a multi-dimensional network of interconnected nodes. So each space is actually a node. So on the left, you can see it's a simple 3-node system, and there we actually can actually see that we have the lobby, we have the matchmaking space, and we have the playing space. It doesn't look like the earlier picture because they're actually all separate from each other, because this is a decentralized system. And on the right, we can see that we can use our visual tools to create as many spaces as you want to. We can create thousands of spaces, millions of spaces, and they're all just interconnect at the edges. So it's a truly massive multi-dimensional network. What's interesting about What's interesting about this network is that every node in the network has no insight into any other node. So the lobby space has no insight into the inner workings of the matchmaking space or the playing space. It just knows that it can talk to them, and they actually work on the edges of using something similar to what we would think of as an API. And through that, we can create very complex structures where we can localize the code in various black boxes, and then actually allow them to speak to each other. All you need to know is the input and outputs, really. And that's the only thing that each space knows about any other space. Also, the way we operate is every single node is spun up as a Docker container using things like Kubernetes. And that means we can visually describe and build out the software of each node and spin it up instantly. And so we internally coined the phrase the Trixta net, which I know isn't popular yet, but it's something we are working on. But using this methodology, because every single node is totally decentralized, anyone in the world could actually build their own node, and then they could agree to allow other nodes to interact with their nodes. And all you would need is the other node to have the rights and to authenticate them, and then those nodes could actually be speaking to each other. So you could have anyone in the world building out software using the Trixta platform, building out their own nodes, and then these nodes could actually interoperate. And that means you could use every single machine in the world operating nodes. They could all be speaking to each other. And that gives you the same kind of scale you would have as the internet itself, which I know is kind of amazing, isn't it? You know, it's the opportunity of building, in the longer term future, it's the opportunity of building out like massive interoperating systems where either people could build nodes, or you could wrap existing systems in a node as well. So you could bring other types of earlier systems into this. So you could take a system that has APIs and wrap that in a node, and then nodes could also speak to each other. So I'm just going to show you a few little aspects of spaces. So So the way our system works is you can literally just design these spaces at will and just put them in there. You don't have to do any coding to actually make a space happen. And then we have a concept of roles and actions. So every space is its own context, and in that you could have role players, and those role players would have certain actions that they could actually undertake. And so here we see we have different roles. So we have a builder role. The builder is the person who actually comes in, or people who come in and actually write code within this, or actually do some of the logic. And we also have other types of roles. So in the larger space, we have something called the Matchmaking Handler. So that role is enacted by an agent, and that agent handles the interaction between the outer space and the matchmaking space. So even though in this particular case this would not be a human, we personify the role to make it sound like it's a person that's doing something, but it's really an agent. And the agent is actually enabled by the matchmaking space. So by interacting through the matchmaking handler, you can actually get this particular black box to do certain functions inside of the space. I mean, feel free to ask me any questions if that sounds like not too clear. These are various actions that one could take. So in everything I've shown you now, there was no code used to actually build any of this. This is really just visually describing these different aspects. But under the hood, we're obviously building up the code base of what this really means through these definitions. And so when you have an action, the action could either be operated through code itself, or you could use the flow system. So this particular flow system shows different aspects of the game itself. It's actually the game. So I mean, I won't get into all the details of this, but we've invented a new way of actually describing flows. And these big things over here really are, if you look at this one over here, it's actually a loop. So things just keep on happening. So every time somebody makes a move, it loops and loops and loops and loops. This is a functional system, so the real looping is actually done through recursion and not through looping. But abstractly, it's the same as a loop. And so we were able to actually show us, that way. What's interesting about this is that this visual representation is actually code. So Elixir is interesting because it allows you, it's a meta language that allows you to create other languages. So Elixir was built in itself as a meta language on top of Erlang. And this is actually a visual language, which is also built through Elixir's meta language mechanisms. So this visual language is actually the same as underlying code, and actually can be described in code. In this particular case, we actually built this visual view by actually taking real code first. So we didn't build this particular view in the visual language, we actually built it in code. But because they're interchangeable, you can move between code and the visual language. So you can make changes in the visual language, and that will make changes to the underlying Elixir code. Unlike traditional drag and drop systems, where you have a lot of wasteful, code that's just generated, this is very tight. It's very functional. It works very. It's very real and true to the underlying code system. So, as humans, we have a problem because we think that we are all knowing and all seeing, and when we write software, we try and use we actually try and believe that we know exactly how the software is going to be built, but because we're only human, we can't really do that. We have to find new ways of describing what the software is going to be, and then once it's been described, we can allow it to build itself in some way, or allow human actors to come in and build different pieces of it. And so we invented something internally called goal-oriented design, where you actually set the goals of your software, and through that, and that's by describing the circles, by describing the roles, by describing the actions. You haven't really written code yet, but that allows your team, or even distributed teams or gig teams, to come in and actually fill in all the different blocks. And because it's built in a way where you can make a lot of changes whenever you want to, and then it would allow you to make changes onto the live system, you can keep making changes to the underlying code base. There are ways of testing and making sure that it's safe to actually deploy, but once you do, it's automatically available to all the participants in the system. This really allows us to build a distributed group of technologists who can actually interoperate with anybody's code. So whether our team builds the code or other teams build the code or Gigsters build the code, by having this framework of designing the software in a goal-oriented way, it basically sets the scoping of all these different small pieces and allows you to distribute them out there to your own team and to others. Using this mechanism, Trixta will ultimately allow us to connect to IoT devices, to cloud services, to machine learning models, anything that's out there. And that's enabled by the fact that our protocol allows you to build massively scalable, distributable systems where there is no limit to the actual number of participants. Thanks very much.